Thanks, Saurabh. Oops. Okay, I'm going to be talking in the context of clouds, but a lot of what I say is general and will hold for any kind of sprays of droplets in any supersaturated or slightly subsaturated environment. So to describe a cloud only to the limit that we need in this talk, a cloud is of course a turbulent flow. If you've flown through a cloud, you know this. It contains aerosol particles which are very crucial to the formation of rainfall, because droplets need aerosol particles to sit on them to be able to condense onto. So if you did not have any aerosols, then there would be no condensation at these small levels of supersaturation. So you then get droplets which are inertial, namely they're slightly larger than point particles and they have therefore inertia of their own, and that will be crucial to what we are talking about. And then because things condense onto aerosol particles, and because when external dry air comes in, things evaporate, there's a lot of phase change in either direction going on in a cloud. And of course, there's much, much more to a cloud, like radiative heating and so on, and we will not talk about them. Today, we're going to talk about what turbulence does to the droplets and what droplets do to turbulence. And they share a complex relationship, as we shall see. So this is the work of all of these people. In particular, Kruur did his PhD recently on this work, and Jason and Lokahit are doing a lot of simulations which are taking the work further. And Samriddhi is my colleague who's a co-worker in all of this. So first, let me describe this thing called the droplet growth bottleneck. Let's try to understand what that is, and then we'll see where turbulence comes in. So suppose you have a droplet sitting in still air, and the air is supersaturated around it. So condensation is going to increase the radius of this droplet very slowly. So the water vapor is then diffusing onto this droplet and condensing onto it. Simultaneously, latent heat is given out, because every time there's condensation, latent heat is given out. So you have an increased temperature next to the droplet. So if it was slightly supersaturated before, it becomes less supersaturated now, or even subsaturated. So further condensation slows down due to this temperature change. And so you have this complex relationship between temperature, phase change, and diffusion. So suppose you had diffusion alone, what would happen? How big could this droplet grow? Now, aerosol particles in the atmosphere are about a micron in size. So like we start from something like a couple of microns, and you see that for a 1 centimeter raindrop, it's going to take like a year. It's going to take a very, very long time for a 1 centimeter drop to form by diffusion. And with latent heat, like I said, the process slows down. And so even to get up to something like a millimeter, it's going to take many days. And so you know that diffusion cannot explain the growth of raindrops. Okay, so let's go to the other part of the bottleneck. So one thing I'd like to say here is, in order to grow from 1 to 10 microns, it takes only order of a minute. So you can, a droplet can grow from 1 to 10 microns in practically no time in a reasonably supersaturated environment. And so we will say that all aerosol particles have now become droplets of 10 microns. What next? Diffusion cannot do the job. What about gravity? Okay, so these drops are slowly falling under gravity. They can mop up smaller droplets which are lying in their way. And please note that for a 10 micron drop to become a 1 millimeter drop, it has to coalesce with 1 million of its fellows to become one 1 millimeter drop. So that is a tall order, as we will see. You can actually write this equation down on the back of an envelope. And this is the time for a droplet to grow from some radius r to another radius r2. You will see that this time is a very, very long time for small droplets. I won't go into all of this, but I will just say that you can work out on the back of an envelope that there is less than 1 collision in 10 to the power of 5 seconds for a 12 micron droplet. So a 12 micron droplet cannot very easily collide and coalesce with a million of its fellow men and become. So basically you just see a droplet of size r, descending slowly, and it's made up of, the sky is made up of lots of 10 micron droplets. So like how does it, what is the rate of collision for a droplet who's slightly bigger? Of course, if he's smaller, he won't collide with anybody. So gravity works for larger droplets of more than 50 micron. So if you have a 50 micron droplet, it can grow to 1 millimeter in 200 seconds. And a lot of people have looked at this regime, and some of them are in the audience. So then, let's go to part 3 of the droplet growth bottleneck, enter turbulence. So we saw that for a droplet to grow to 10 micron, it's very rapid by diffusion. 50 micron onwards, it's very rapid by gravity. What happens between 10 and 50 micron? And this is where a lot of work in turbulence is going on to try and understand. So you have a preferential concentration, as you can see, of the droplets. Turbulence causes this. So for students not familiar with this, it's kind of counterintuitive, because unlike, sugar in your tea, which if you stir becomes homogeneous, this started out with a homogeneous distribution of droplets but became inhomogeneous. So you'll see that droplets are concentrating preferentially in regions outside vortices, and this is something you should remember. So then, based on this increased number density outside the vortices, people have come up with estimates for enhanced collisions of droplets, and the more they collide, the more opportunity they have to coalesce. And so for droplets which are greater than about 25 micron, you can explain some of the fact that droplets grow very rapidly to this. So incidentally, we talked about a minute up to 10 microns, a minute for 52 droplet, 52 raindrops. 10 to 50 seems to occur in about 10 minutes. So this growth seems to occur in 10 minutes, not in months or whatever. Remember that a cloud lifetime is about an hour. So you need something to happen in 10 minutes. Some part of this may be, some part of this may be explained by the fact that after 25 microns, you have a lot of enhanced collisions. But if you see like the recent paper of Wilkinson, or you do some back of the envelope calculations, you will find that by simple turbulence argument, if you have a 10 micron droplet, its Stokes number based on the Kolmogorov scale is 0.05. Namely, its time scale is 0.05 times the Kolmogorov time scale. You will see that this preferential concentration is too low, so growth rates are too slow, and they cannot be explained. So basically, how do you get from here to somewhere around here? And that's the question I'd like to address today. And we are proposing vortex evacuation as a mechanism. We've shown it analytically, and we've shown it in 2D simulations, and we are in the process of looking at it in 3D simulations, which is why I've put a question mark there. And even the 3D simulations that we are doing are nowhere near a Cloud Reynolds number. So that's why I put a question mark there. And what is vortex evacuation? So basically, we are looking at one-point vortex. Let's start by looking at one-point vortex and write down the dynamics analytically. So droplets around there can be described by the Maxey-Riley equations, which basically say that if a droplet has an inertia, it follows the flow but with a reluctance. And this reluctance leads to a centrifugal effect. So basically, small droplets slowly spiral out of vertical regions. They're very, very slow because they're very, very small. So remember, we're talking about 10 micron droplets and asking how they grow bigger. In this problem, for a point vortex, we chose this length scale. This was Kruger's genius. He chose this length scale, which goes as the time scale of the particle relaxation time, which is in milliseconds for a cloud, by the way, and the vortex circulation raised to the power of half. So this is a special length scale, And when you write the equations in this length scale, you get a parameter-free set of two very simple ordinary differential equations. B of t represents how big the droplet is. So it would be 1 at 0 time, and it would become, bigger and bigger as more and more droplets join this. And zeta is the angular momentum of the droplet, which very quickly relaxes to the flow angular momentum. So basically we are left with how the radius, what the radius of, and this is not the radius of the droplet, this is the location, distance from the vortex that we are talking about. So we are asking how this droplet is moving in the vertical region. Okay, so now these equations actually have a boundary layer structure, and that's the key thing in this talk. Because they have a boundary layer structure, here's the vortex. We talked about a point vortex, and here's the distance r away from the vortex. Close to the vortex, we can write a separate equation. Far away from the vortex and at long times, we can write another equation. So you have an inner solution and an outer solution, separated by something of radius of order 1 in the length scale that I talked about. So for different droplets and different vortices, this length scale would dimensionally be different, but in non-dimensional terms, it's 1. The inner solution, we'll come to this, but the important thing I want to say here is that up to a radius of 0.5 in our units, you can have what is known as caustics. So if you're writing the droplet distribution as a field and trying to get answers, you will be completely wrong in this region, because droplets may not be described as a field over there. Basically, one droplet can catch up with another droplet, and this is called caustics. They can catch up, because it can catch up with another droplet. You can have two velocities at the same place and same time. And that means it's not describable as a field. So that's the key point here. It is not a field in this region, but bizarrely enough, after a radius of 0.5, you can describe droplet dynamics as a field, because one droplet will never catch up with any other droplet. So they can slowly come together, but they will never catch up. So this is the difference between the inner solution and the outer solution. You can solve those analytically, and you can get a del dot V of the particles, which means, remember, the flow is incompressible, but particles can, come together, and they live in a compressible situation. So I'm pretending now it's a field, and I'm writing a del dot V particle for it. When I do that, and as I said, this is a singular perturbation problem. In other words, it has boundary layer structure. So the del dot V inside the inner layer is large and positive. That means the vicinity of the inner layer is very rapidly evacuated by the particles. So in fact, in a particle time scale, that means in milliseconds, this vortex thing is evacuated. So this is what happens in the inner layer. So the vortex becomes empty. Actually, Raymond Shaw had recognized this a while ago, although he didn't think of it in caustics language. He realized that it will evacuate rapidly, and especially in intermittent vortices, you'll have an effect. In the outer layer, the del dot V, namely the divergence of the particle velocity vector, is small and negative. That means particles are slowly coming together, and at some time or other, two droplets may touch and coalesce, but this is going to be a rare event and nothing much happens. So what we are basically summarizing is that if you want like a vortex to produce a lot of collisions and coalescence, then you have better depend on the inner layer. So this is the central message here. Okay, so then what I'm showing here is that if you, okay, so we've done this simulation. Let's start with that. In this simulation, we've colored in green particles who are sitting inside the special radius that I talked about. And I've colored in red particles that are outside, or rather Deepu has colored them in red. So when I run this movie, you will see how the inner layer evacuates. More than that, every time a particle collides with another particle, with some probability we've made them coalesce. So when they coalesce, if one of the two coalescing droplets comes from the green region, we'll color it blue. If they both are red, we'll let it remain red. So and as droplets become bigger and bigger, they'll centrifuge out faster and faster. So like the bigger droplets will reach a greater distance. So we'll ask how many of them started from the inner region and how many of them started from the outer region. So here's the movie. You can see some droplets already becoming blue. So these are what we term Caustics droplets. They came from the inner region being evacuated quickly. And as the movie proceeds, you'll see that a vast majority of the big droplets, in fact, almost all the big droplets come from within this region. So this is a mechanism for triggering droplet growth, which is absent if you treat the whole thing as a field. And the interesting thing is it's going to occur even for the tiniest droplets if you have a strong enough vortex. That's all that you need. And so then we put a small amount of polydispersity in these droplets, and that helps, you know, grow it much, much more. And so you can see that this was the initial distribution of the red droplets, and centered around a particle radius of 10. This was the initial radius of the green droplets. And very quickly the black droplet, namely the blue droplets, have become larger. So they have actually grown by a factor of 2. In this simulation was run for 0.044 seconds, so 44 milliseconds. So it takes an extremely short time for a small number of these particles to become larger. And all you need is a few seed particles which are larger, who will then, you know, get this cascade process going. They'll mop up other droplets with greater ease and become bigger and bigger very quickly. And this I showed you in 2D, but it's enhanced a lot by vortex stretching. And if you'd seen Lokahit and Jason's poster, you would have seen that. So then we can actually analytically write down probabilities of collisions and recollisions, and we can see how fast droplets grow. And our analytical prediction is very, very close to the simulation. So basically the moral is that caustics win. Okay, so now we have done a 2D simulation with point vortices, but you can do this with, you know, viscous Gaussian vortices, and the answer won't change much. You can see everywhere a special caustics radius up to which everything is evacuated, and Kruger has computed these densities by a special method. The color shows particle density. So wherever there is red, there's lots of particles. And you can see that we've chosen, like, these two together make up all the particles. And you can see that the red color is everywhere. So in other words, at the caustics radius, you have a very increased density of particles. And so a lot of collisions can happen there. And this density increase is at least an order of magnitude. It's even bigger for a Burger's vortex. So particles live on this special radius. That's the summary. Okay, so now, like, what happens in 3D? So what we're trying to do here is to find resemblances in 3D. Remember, we need fairly strong vortices for this to happen, and all our 3D simulations are so small that we cannot get very powerful intermittent vortices which exist in a cloud. But even with these weaker vortices, we see signatures, or signature may be too strong a word, we see resemblances of everything that I've talked about, and we'll see what that is. So like this is just a demonstration where Jason has plotted high rotation and high strain isosurfaces. So the blues correspond to high rotation and the reds correspond to high strain. In the gradu language, this the rotation is 2 and the strain is also 2. So you'll see that the strain regions, if you stare hard, are forming sleeve-like things around the rotation regions. And the important thing here is high strain regions are very close to high rotation regions. They are interwoven pretty nicely. So how do we use this? So then in this simulation, I'll spend a minute or two on this page to explain what's going on. So we've done simulations at a Stokes number of 0, that means tracer particles. Then 0, 2, 0.1 and 1. Cloud particles live somewhere here, but because we are working with weaker vortices, cloud particles could even be, cloud droplets could even be at a slightly bigger Stokes number than this typically. Okay, so then in this, the color shows you where the droplets live. And you can see that 99% of all droplets live inside this green line between an R and an S, a rotation and strain of 0.8 respectively. So 99% of all particles live in regions where the rotation and strain are within this limit. So, and you can see that if you look at what is the ratio of RNS in the flow, you'll see that tracers represent RNS in the flow. Tracers are everywhere there is an RNS. So there's no difference between Stokes equal to 0 and the actual RNS of the flow. So then you can see that it's fairly symmetric in RNS. The black dots show where collisions occur. And where collisions occur is also mainly in the regions where RNS are occupied. So this is nothing special for non-inertial droplets. Now, when you add a teeny bit of inertia, and remember cloud droplets have Stokes numbers like slightly bigger than this even. When you add a teeny bit of inertia, you immediately see that more particles occupy more strain regions. So it's not symmetrical anymore. So more particles occupy strain regions. But remarkably, the collisions are happening where there's very, very few particles. So you're getting collisions in extremely high strain regions and in low rotation, far more low rotation regions than where the particles live. So where particles live, even if they're clustered in R and S, is not the same as where they collide. Where they collide is in regions of higher, lower R. Accentuated when you go to the next Stokes number of 0.1, where you see a huge number of particles actually colliding with each other at large strain rates. When you come to a Stokes number of 1, the picture changes because now particles are rushing around from one vortex to another, and there's no preferential lifetime spent in the vicinity of one vortex. And so you again see them, exploring all of RS space, except that the number of collisions is way, way, way more than that one. So otherwise, the picture is pretty similar to a non-inertial situation. So you have huge numbers of collisions. Okay, so then what does that buy us? What Jason has done in this is something very simple. He has looked at the time taken by a particle to evacuate a vortex before it collided. In other words, take a collision, translate backwards in time the trajectories of the two droplets who collided, and see when they were living in a vertical region, when they were last in a vertical region. Oh wait, I'm showing the other one. Yeah, so this is what I want to talk about. So then ask what was the time, when was the time that it came out of the vertical region, and how much time before the collision did it spend in the straining zone. And you will see, and this is in units of Kolmogorov time, which is a very short time. It is, like some 50 milliseconds or so for a cloud droplet, for a cloud flow. So you see that in 2 or 3 Kolmogorov times, practically half the particles have actually collided. So they collide very soon after leaving the vertical region. And this thing is even shorter in time for the slightly bigger Stokes number, which is also representative of cloud particles. So the time they spend in the straining zone is very short before collision. So most collisions, a large number of collisions occur soon after particles have left regions of high rotation. So we still have to work further to take this to an exact description of the caustics thing that I told you. That will take a little bit of work. This is ongoing work. Now we'll go back to the other thing, which is how long did this droplet who came out of a vertical region actually spend in that vortex? We were talking about rapid evacuation. Was that true or not? And you see that that is very much true. Like this droplet spent very little time in the vertical region, especially when there were high levels of rotational flow. When there was high vorticity, the particles left the scene in much less than a Kolmogorov time. And that is even more heightened at Stokes number of 0.1. So basically, particles are rapidly evacuating regions of high vorticity if they find themselves in regions of high rotation. And so Q actually is representative of tube-like vortices. So it's not, the shear kind of vortex. So then you can see that they spend very little time in that place. They evacuate quickly, and then they go and they have a good chance of colliding pretty soon after that with another droplet. Okay, so in the last 5 minutes, I'd like to talk about the reverse. Up to now, we've talked about how droplets responded to turbulence, what turbulence did to droplets. Now we want to ask, what do droplets in their turn do to turbulence? Can they do anything to turbulence? And the instinct would be to say no, because droplets are in an extremely dilute suspension. They're extremely, extremely small. Their volume percentage is 10 to the power minus 6 in the flow. So you would say, okay, like they're so small that even if they're tiny and heavy, they're going to do nothing at all to the turbulence whatsoever. So they're just slaves to the turbulence. We're going to see that phase change changes the equation between them. And phase change brings about a complex relationship between them. So we can see how something of 10 micron, which is like orders of magnitude smaller than the Kolmogorov scale, is going to affect the flow. And that's what we've solved this set of equations here. So seen in blue is the Navier-Stokes equations, and they are modified by buoyancy effects due to temperature changes. Temperature is the winner over here. So then we solve for the temperature field with a source term due to condensation and a sink term due to corresponding sink due to evaporation. We solve for the water vapor field. We solve for the liquid. You'll notice that we solve for the liquid slightly differently because it has inertia. So we have expanded this thing to the first order in Stokes. And that is wrong. We're treating it as a field that is wrong inside vortices. So we can also solve the Maxey-Riley equations for individual droplets. So we do both of these depending on the situation. And so we have this quantity H which takes care of whether it's evaporation or condensation. The droplets are growing, which changes their Stokes number. So the droplets are growing slowly in time. There are like 8 non-dimensional parameters at least in this problem, but the 2 important ones that we find that there's 2 of them who are important, namely the time scale of the phase change and the time scale of the particle itself. And we can create an effective Atwood number, namely a buoyancy, total amount of buoyancy created, which goes as the product of the square roots of these 2 time scales. I don't have time to tell you why, but we can discuss it later. And you need intermittency to create this kind of Stokes numbers. So like the stronger vortices will do this much more easily. And then this is a movie I'm going to show you. Basically, inertia makes the droplets evacuate vertical regions. We're starting with this kind of vorticity pattern. We're starting with uniform temperature, saturated water vapor everywhere, and no liquid water. And then, or maybe a small amount of liquid water everywhere. So then we're going to see how droplets leave the vertical regions, and then they undergo condensation because it's supersaturated elsewhere. The condensation gives rise to temperature changes. So the temperature, the flow outside the vortices gets heated up, leaving cold vortices, and these cold vortices then are going to change the dynamics, like give buoyancy, and they're going to feed into the turbulence. So there's the movie. We started with a uniform temperature field, but you see cold vortices being created. And so liquid water is preferentially living inside this, living outside this. There's condensation preferentially outside. So this is the central message here. Okay, so what does the resulting turbulence look like? This is the normal flow when we didn't have droplet inertia and the rest of it. And here's the droplet-laden flow. So you can visibly see small scales over here. And if you plot the spectrum, I cannot come to a turbulence meeting and not show a spectrum. So I put this in over the last 1 hour. So basically, although the process is unsteady, remember that the turbulence may be in steady state, but the droplets are not in steady state. The droplets are becoming bigger and bigger, and the water vapor is getting more and more eaten up as time goes on. In this flow, we can create other steady state flows, but we're not. The droplet size, they started out as 10 microns. In this thing, it would be like yeah. It would be very small, way smaller than Kolmogorov. So you can see how the spectrum changes with and without droplets, although the droplets are minuscule, as was just pointed out. Okay, so one mechanism for this, for how droplets change the thing, is if you have two vortices who are oppositely signed, you know they will go down by Biot-Savart law. So now we'll see what happens when these become cold vortices. Immediately you have Kutta lift. There's many such mechanisms we have worked out, but I don't have time to talk about the rest. So just watch this movie. This is what the droplets, this is what the two cold vortices do. So you create, and in the movie that we had of the full 2D turbulence, we could pinpoint situations where things like this were happening. We can go through this step by step later on. Okay, so we had that Atwood number criterion for when this should happen. We see that the two vortices do this funny behavior when the Atwood number satisfies our simple criterion, and they do not when they do not. So here we have a mechanism for cloud droplets who are way higher in K to produce buoyancy, which will affect Kolmogorov and bigger scales. And that's what we are seeing over here. And that's the summary, and thank you. So basically, I showed that vortices seed droplet growths. Droplets return the favor by messing with turbulence. Thanks for your attention.
Questions?
Okay, I don't want to, talk about the slope in any detail because this is unsteady flow at every time, but this is a typical spectrum. So, I mean, for some time, this kind of spectrum is held. This is just -3 just put there. It's 2D simulation. This is -3 just put to guide the eye, but, we don't have, enough. The Reynolds number is 20,000. I don't want to comment on the slope.
The particles as some kind of scalar field, then there could be faster coalescence because of the inverse cascade kind of stuff. So that could speed up the coalescence, treat them as inverse cascade of scalar field.
No. See, inverse cascade means, let's say, bigger structures are being formed. The droplets don't know about it. They're micron sized.
They will be carried by a scalar.
Yeah, they'll be carried somewhere, but they will not, they're too small to meet other droplets. It's a very dilute suspension. So just being carried from place A to place B doesn't mean they meet each other. You have to have a mechanism for increasing droplet densities very much. And for tiny droplets, that mechanism doesn't exist by the standard preferential concentration.
What's the Reynolds number of the droplet?
It's way less than 1.
Okay, so actually what I have,
something like that. We've calculated it for a range, but it's way less than 1 all the time. Yes.
How will this mechanism change if we change the type of aerosol on which the droplets are condensing?
Yeah, so like you mean like something which is hygroscopic or something which is...
Yes, precisely.
Yeah,
yes.
like if you have aerosols which repel water, then it won't happen at all. But if you have aerosols which like water, then it will happen. And if you have aerosols which are very big to start with, then you're going to have a lot more of this happening. In fact, in polluted environments, what is seen is that you get a very large number of droplets, but because there's so many aerosols, the supersaturation is eaten into. And so you have very large number of very tiny droplets who then cannot become raindrops. So if they don't reach 10 micron or whatever, they can never become raindrops.
Thank you.
wonder what's the effect of thunder on this phenomenon.
I don't know.
Because it would differentially affect droplet size.
Yeah, yeah. Yeah. So in this, we've actually neglected things which are very high up in the atmosphere. We're working in a place where, you know, like a kilometer or two up in the sky. Why are the vortices formed? Because the whole thing becomes turbulent. Effectively, you're getting chemical energy which is in the droplets, which is in the water vapor, converted into heat energy, I mean basically potential energy due to condensation. And this potential energy is getting converted to kinetic energy. So it's effectively buoyancy of the rising thing, the rising cloud.
Okay.
That's a global scale. Yeah, yeah.
Where do they appear?
So like now we've forgotten about the large scale. We are living in the close to Kolmogorov scale. And we are asking like what happens to droplets? Can they, you know, grow bigger? And when they grow bigger, what do they do to the, you know, smaller scales in the flow? Yes, so it's like, I mean, except for the droplets, it's normal homogeneous isotropic turbulence. So when I shut off the droplets, that's what I have.
You still have very scale disparities. Okay, I'll talk to you.
Okay, it's the temperature field which does it.
Yeah, I had just a question about the temperature field and related to what Srinivasan asked. Now, you are actually releasing heat because of phase change. And normally, well, I still don't see how to non-dimensionalize the heat release that you observed in your work. But normally, heat release changes the vorticity, and in fact, usually by orders of magnitude.
Yes.
It increases the vorticity by a mechanism through the baroclinic torque.
Yes.
Once you have temperature gradients, you have a baroclinic torque. The baroclinic torque is a source of vorticity.
Yeah.
Okay, it's not just collecting vortices from mud layer, but it's actually creating new vorticity.
Yeah.
How strong is that effect in the kind of analysis that you've made?
So here too, it's baroclinic torque created due to various reasons. So like the small scales are all created by baroclinic torque effectively. But given, you know, the size of our simulation and the number of droplets, it's not an order of magnitude type effect.
How do you look upon that? You look upon that as in fact that there is not a great deal of increase in vorticity, or that there may be other sources of increase in vorticity.
Basically, this tells you how much vorticity, I mean, how much kinetic energy has increased. So like the large scales are unaffected and the small scales are increased by some small amount. So it's not an order of magnitude. Yeah. Yeah. For these droplets? Yeah, you can treat it as infinity. They're just, you know, falling under gravity. They're basically not diffusing. They're 10 microns. Thermal Peckley number is same as the Reynolds, 7. Yeah, it's Prandtl number of 1. So, yeah.
I had two questions. One is, I understood the stuff about the vorticity and shocks, but then suddenly you put strain also. So what happens that time? I mean, you said something enhances because of the strain near the vortex or something like that.
No, no.
You had rotation and you had those two contours.
Okay, okay.
One of rotation, one of strain.
Okay, okay. So I should have explained more. So we did this analytical work where there was only a vortex and nothing else. So there was no region of strain. There was only a point vortex and the rest of the flow was irrotational, or it was a very small vortex. And there we got this shock thing which is happening. Now in a real turbulence, that was a 3D simulation of actual turbulence, you have rotation and strain completely intertwined. So we are trying to connect this shock thing to something there. And that's why I called it resemblance. So we measure, where the collisions occur, and we say, okay, like if it is occurring in the rotational region, then it's not, our kind of collision. Our kind of collision is one which would qualitatively leave the rotational region and immediately within a short time coalesce or collide with somebody else. So this is what we are measuring there.
And of course, the other comment I probably have always made to you is that there could be very interesting applications in planet formation.
Yes.
And it'd be good to, you can start a different...
Sit in Pune and talk about it.
Yeah, so no other questions. Let's thank the speaker for the engaging talk.